Welcome to this video, and in this video I wanted to derive an equation and do a calculation to find the size at which a minor planet, dwarf planet or asteroid actually gets big enough to become spherical. So that's what we're going to do in this video. Now, before we do that, one of the definitions of a planet is that it has to have sufficient mass to assume hydrostatic equilibrium. So that basically means that it becomes spherical. Now, there are a few other classifications for which basically the International Astronomical Unit has given for the definition of a planet, but one of them is that it has to be spherical. So you can't get potato-shaped planets, for example. They've got to be a certain size. And some of the other ones means that it's going to orbit the sun or a star, and other ones that it clears the area out. But the one we're interested in today is its spherical shape, essentially. So on the left-hand side, you've got Venus and Mars, they're planets, and on the other side, you have a couple of minor planets which are essentially not planets. And these are small enough that they don't assume hydrostatic equilibrium. So this does actually include objects that are not planets. So here we've got Pluto and Ceres. These are not planets. They are actually classified as dwarf planets. Now, Pluto is a bit bigger than Ceres. Ceres is actually at the limit of what can be spherical. So we're going to calculate this actually towards the end, and we're going to find out how close Ceres is to the theoretical limit of being spherical, and it might surprise you actually. So before we get started, let's start with the hydrostatic equilibrium, what that is. Well, hydrostatic equilibrium is when the inward gravitational forces trying to collapse the object are going to be balanced by an opposing pressure gradient. And it's this starting point that we're going to use to derive our equation, which can help us find the point at which it's going to become spherical, when those gravitational forces become large enough that it will mold it into this spherical shape. So the first thing we're going to start with is we're going to consider a small slab within the planet. And it's probably worth noting that for this, we're considering a rocky planet. Okay, if you've actually got something like a gas giant, then it's way above the limit anyway. So we're going to consider a rocky planet, and we're going to consider a small slab located inside the planet, and it has a thickness of delta R. So this slab has a thickness of delta R. It's also located from the center of the planet at a distance of R. So we've got delta R, the thickness, and we've got R, which is distance from the center. Now, in our calculations, we're only going to consider gravitational forces from material inside that radius, so up to R, basically. So the material closer to the center exerts a gravitational force on this slab. The material that's further out doesn't contribute to any net gravitational force, so we only consider the ones inside for now. Okay, so if that slab is there within the planet, then basically the pressure from underneath is going to push the slab upwards, while the pressure above the material is going to push downwards, which is our yellow arrows there. So we've got pressure pushing on that slab from above and below. And if it's at rest, then it means the gravitational force must be slightly greater than the pressure above because it's not moving anywhere. So it's got to be balanced. Those pressure forces have got to be balanced. So that is an important thing here. So what this means actually is because you've got a different gravitational force compared to the pressure, it means that the pressure must increase with increasing depth. Otherwise, the planet's going to collapse. So as you get deeper down in the planet, it means your pressure is going to increase as well. So we now need to get an equation for the pressure gradient. Well, also it's going to relate our pressure gradient and the density of the planet. So again, this slab has a thickness of delta R. It's at some distance R from the center, and it has an area of A. Now we're going to assume that the planet is a perfect sphere. We know in reality that's not the case because the planets are rotating and actually slightly wider at the equator because they're slightly squished because of their rotation. And they have some delta rho and some pressure P. And the P obviously depend on R. So we can now write the volume of this slab, which is going to be the area times the thickness. So we've got the area of the slab, and then we've got the thickness, so we can then get its volume. And if we've got the volume, then actually just multiplying that by the density is going to give us the mass of that slab. So we've then got an expression for the volume and the actual mass. So then, the gravitational force acting on that slab can be given by this equation below. So we've actually got so it's Gm m over r squared. So you've got the mass of the planet within the radius r. So for any mass that's below r, and then you've got the mass of the slab, and then you've got the radius squared underneath. But we can exchange that mass of the slab for what we have at the top instead. So we can actually use the A delta R instead and take the M slab out. So we've got the gravitational force that is acting on that slab within the planet. Now, we now need to consider the pressures because it's going to be balanced. So the pressure of the material below the slab is going to exert an upward force, which is going to be equal to the gravitational force times the area of the slab. So that force from the pressure is the pressure and the area times together. So that's what we have on this side here at the very, very front. We've then got an additional downward force from the pressure. So this is above the slab. So this time around, you can see that actually the pressure at that location is going to be plus the delta R because it's the thickness of the slab. And obviously times the area gives you a force. But this time, because it's a downward force, it's going to be negative. And we've already got our gravitational force there. And because it's in equilibrium, it's not going anywhere. It means all the forces must cancel out. So we can equal that to 0. So we've got two pressures, one pushing up, one pushing down, and the gravitational force, which is going to be pushing down as well. So the pressure that's going down is in the same direction as the gravitational force. And that's why the pressure pushing up is slightly more than the gravitational force. Or the other way around, sorry. Okay, so now what we can do is we can actually take the A out, the area, because it's on all of those bits there. So we divide by the A, that removes it out. And since this is actually a difference in the pressure, because it's a pressure difference across the slab, we can write it as delta P instead. So actually what we've done there is we wrote delta P at R is equal to the gravitational force at the same location, basically. So we've now got this expression here for the difference in pressure across it. Now what we can do then is we can move the delta R across to the left-hand side by dividing it all by delta R, and then we have this expression in the middle. Now, if we assume that the delta R, delta P are going to be very, very small, so almost infinitely small, we can write that in the form of a differential equation, which is given at the bottom there. So now we've got a differential equation at the bottom. And this is basically going to be our basic equation for hydrostatic equilibrium of a sphere. And actually that's useful for a variety of things, not just planets. So we've got this equation for hydrostatic equilibrium. Now what we're going to do here is we're going to try and solve this, but in order to solve this, to see what happens to the pressure with the radius within the planet, we're going to assume that it's made up of lots of thin shells. So instead of just a slab this time, we've got thin shells that go all the way around. So whilst this is a 2D image, imagine it to be like, the skin of a ball or something. So you've got a shell, okay, which is the red circle there. So each shell is going to have a thickness of delta R, same again as what the slab has. So we've got delta R, thickness of our shell. The sum of the mass of all of the shells within some radius R is then going to be the mass at less than radius R. So that's the same thing basically. So they should all add up to the total mass essentially. Now the mass of a single shell can be given as 4 pi r squared times the density times delta R. But if the thickness of the shell tends to 0, then the sum of the masses of the shell becomes the following integral. So we can write it in an integral form here. Now, we're going to make some assumption about the density and how it depends on the radius. Now, we know that the density is going to change. Realistically, in the real world, the density is likely to get greater towards the center, okay? But we need to make some assumption of that first. We're actually going to make some assumption that actually it doesn't really change. We're going to assume it to be constant and assume it to be independent. So this is a fairly simple assumption to make, but it's going to make things a lot simpler basically. So this time around, we're not going to consider the density changing as a function of r, but we know in reality that is likely to be the case. So if that's the case, we can actually then exchange our mass. So we had an expression for the mass within some distance r from the center, and we can put that down here instead. And we can put it in our differential equation that we had for the hydrostatic equilibrium. So what we're going to do here is we're going to assume that the pressure at the surface is 0 and that the radius at the surface is rp. And we can then actually write this in the form of an integral. So we can then look at solving it. And we're going to integrate between the surface and some distance r, and the pressure is going to be going from the maximum pressure to 0 basically. So we've now got this integral at the bottom. So if we actually integrate that, we should get the following solution. So we get this for the pressure. And what we should be able to see actually is when we go to the center, we're going to get a maximum pressure. And as we go to the outer surface, it goes to 0. So when your r squared becomes the same as rp, then you're going to get a pressure of 0. And the other way around, if r is 0, then you end up with the maximum pressure. So yeah, you can basically see here that the pressure rapidly increases with increasing depth, as we just mentioned. So you can see where your maximum pressure is going to be and where your minimum pressure is going to be as well. Now, real investigations of the Earth show that the density changes by about a factor of 3 from the surface to the center, whereas the pressure increases much more rapidly. So it's not too misleading basically to assume that the density doesn't change. So we can assume, or at least our assumption of the density not changing is not too bad. It's going to give us a good approximation. So the maximum pressure then we already know is going to occur at the center of the planet, and we can write it like this basically. So what we've got here is the maximum pressure which occurs at the center. Now, the interesting thing that starts to happen here is even rock can behave like a liquid under high enough pressure. So it can lose its rigidity and it can behave more like a fluid. And this occurs at a critical pressure. So the central pressure in the planet and the critical pressure are going to be important things we need to know. So for Earth, the critical pressure is 10 to the 9 Newton meter squared, or newtons per meter squared, basically. And the pressure at the center of the Earth, the actual central pressure, using this approximation here, is 1.7 times 10 to the 11. So we can see that the pressure at the center is quite a way above the critical pressure. So that tells you straight away that certain parts internally of the Earth, at least, are going to behave more like a fluid or a liquid than like a rock. Now, there are two regions in a planet or a rocky planet like this that are going to behave differently. So there's like two regimes essentially. One is going to behave like a rock, which is the lithosphere. That is the outer part. So that's going to include like the crust and the upper mantle. And then part of it is the rock is going to behave more like a liquid. And this is the asthenosphere. I think I've pronounced that correctly. And that is the rest of the mantle and a bit further down, where it behaves more like a liquid and can flow essentially. So you've got these two regimes. Now, the lithosphere of the Earth is about 100 kilometers thick, while Mars is about 500 kilometers. So Mars has a much larger lithosphere, but it's also a much smaller planet as well. And this again includes the brittle crust and the upper part of the mantle. And then the other part that behaves more like a liquid is denser. It has it's a weaker layer below this other one, and it's in the mantle between about 100 and 410 kilometers for Earth. Mars is about 500 to just over 1,000 kilometers, and that's down to size and the differences in pressure. A smaller planet is not going to have such higher pressures inside, so depths can change and things like that. Now, there is an interesting consequence here, as we mentioned, because it behaves like a liquid, so some of this inside of the planet is going to behave like a liquid, it means it can flow. And it's going to flow throughout the planet, and it creates a shape with the least gravitational potential energy. So it's going to mold itself into the most favorable shape in presence of that gravitational potential energy. And that's a bit like water running down a hill, really. You've got a liquid there, and it wants to go to a position of lower gravitational energy. And it's the same thing when you've got a large planet like that. Once it starts behaving like a liquid, it's going to then shape itself like a sphere. So what you can do then is you can work out what point this occurs at. Now we can do the calculation. We can already see straight away that there's going to be objects where internally their central pressure is always going to be less than the critical pressure. So the entire body will behave like a rock. Therefore, you're not going to get a spherical shape. So asteroids, minor planets, they're going to have internal pressures that are not greater than this critical pressure. And again, what you can do, if you assume a density of rock of about 5,000 kilograms per cubic meter, you can work out what that radius occurs at. And it's around about 535 kilometers that this occurs at, a radius at least. However, Ceres has a radius which is slightly less than this. This has been measured to 475. So we've done a fairly rough approximation here, but it's fairly close. And Ceres is pretty much going to be at the limit of that. And it could be that the density for Ceres is not what we've used here, and the fact that the density changes as a function of r as well. But nonetheless, it gives us a rough idea, and Ceres is pretty much at the limit for being spherical. So thank you for watching, and if you enjoy, then check out some of the other videos.